Hello students. In this video we're going to be talking about homework problems that contain function inequalities. Remember, inequalities are less than, greater than, less than or equal to, or greater than or equal to. So these are going to be questions that involve things like find the values where f of x is greater than 0 or something like that. So here's a little note that helps us understand kind of conceptually what we're doing here. When we're dealing with function inequalities, we will always be looking at where our function's value is either greater than 0 or less than 0. Or sometimes it'll be greater than or equal to 0, less than or equal to 0. So we're looking at where our function's graph is going to be above or below the x-axis. Let's think about this. If we have a graph, and I'm just going to draw a kind of random function, it might have some ups and some downs. The places where my function's value is greater than 0 are going to be these values here where my function is above the x-axis, right? Because these are all the positive y values. If we're looking for where our function is less than 0, they would be the values below the y-axis. And if we're looking for places where my function is equal to 0, that would be these points right here where my function actually passes through or intersects with the x-axis itself. So if I wanted to find the points where the x values where f of x is greater than 0, I would need all of the points in between the two red dots, but not including the red dots. If I had this instead, I would include the red dots. If I had this, I wanted to find all the x values where f of x is less than 0, I would just want the area to the left of the red dot or to the right. Oh, I guess I should specify. I would want the area to the left of this red dot or to the right of this red dot, but nothing in between, and I wouldn't want to include the red dots. However, if instead I wanted to find this, then I would include the red dots and these directions as well. So that's just conceptually kind of what we're looking at. Let's actually get into an example, and maybe you'll see a little more clearly what we're talking about. This problem comes from the Homework 10A Common version. And in this problem, first we just want to identify whether the degree of the function is even or odd. Well, since our end behavior both goes in the same direction, that makes it an even function. We can identify that pretty quickly. Now let's actually get into the inequality part of this problem. We are trying to find the intervals. Note these are x intervals that represent the solution set for g of x is less than or equal to 0. So g of x, those are y values. And for our y values to be less than or equal to 0, we're looking for the places where our function dips below the x-axis. So it would be all of these right here. And since we're also including 0, so we have less than or equal to 0, we're also going to include these points here where our function is actually equal to 0. So our job is just to write the intervals for the x values that make this happen. And that's just a matter of looking at our graph. So we're going to start at negative 1, 2, 3, 4. From negative 4, which is included, to negative 2, that represents kind of the first chunk of this graph that's below the x-axis. Then we also need a second chunk that includes from 0 to 2. Scratch that, I can't count. It goes from 0 to 1. So it's just the x values. Whoops. It's just the x values from here to here and from here to here that answers this question about the intervals that represent the solution set. The solution set is just our x values. So when we're going to select an answer, make sure you choose the answer that has the right number of chunks, so to speak, and the right brackets on the outside. So we're going with this third one right here, bracket AB union bracket CD. But now we also have to fill in what A, B, C, and D are. So our A is -4, our B is -2, our C is 0, and our D is 1. And since we don't need E or F, we just put not applicable, and A, and A. So that was a kind of visual, conceptual question, but now we're going to actually talk a little bit more in depth about how we do this when we don't have a picture. So just to bolster our conceptual understanding here, there are only two situations where a function can go from above the x-axis to below the x-axis, or vice versa. So I'm going to draw a graph. I'm just going to draw a random kind of squiggly graph. Let's do like this. So our function is above the graph here, 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 and then it's below the graph, below the axis here, here, and here. The only way our function can switch from one side to another is if it passes through the axis. So in between any place where our graph switches, there's going to need to be an x-intercept. We also call those zeros. Now, just because it touches the axis doesn't necessarily mean that it switches sides. Like here, our graph can kind of dip down and touch the axis, but then go right back up. So there can be other x-intercepts involved, but if our graph goes from below to above, or from above to below, then it necessarily has to pass through the axis itself. So these red dots represent what we called critical numbers. X-intercepts are critical numbers. They are places where our graph might go from top to bottom or from bottom to top. There's one other situation where this might happen. So I'm going to draw another graph and draw a function. Let's see if I can do this here. Hold on, let me draw something a little different. All right, so here's our function. You might have seen some functions like this in the past where they might have like an asymptote that they're getting really close to, or even a vertical asymptote. So another type of function where our graph can potentially go, okay, this is getting bad. Gonna redraw this. Another type of function where our graph could potentially go from top to bottom and kind of switch is if we have an asymptote. So this graph switches from bottom to top by crossing over the x-axis. That's a critical number. That's an x-intercept. But also, if you have a break or a jump in your graph, like this asymptote, we can go from top to bottom kind of immediately whenever there's a break. It can happen. It doesn't have to happen, right? So we could have a break in our graph where we're on the top and we stay on the top. That could happen too, but breaks represent places where we could kind of switch down to the bottom. So all of this is to say that we're about to show a bunch of steps to solving these types of problems algebraically, and these are the two situations that we must look for. Critical numbers, which are x-intercepts, and asymptotes, which represent breaks or jumps in the graph. And there are going to be a bunch of steps that we're going to need to do to solve these problems. So this list of steps is important. You might want to snap a picture of this from your screen or pause your video and get all of these written down. The steps for solving a question, like find the solution set for f of x is greater than 0, are First, find the critical numbers and the asymptotes. Critical numbers and asymptotes. These two things represent places where our function could go from above the axis to below the axis, or from below to above. Critical numbers are x-intercepts. So these are the x values that make f of x equal 0. They're the zeros of our function. They are the roots of our function. So we solve these by setting the numerator of our function equal to 0 and solving for x. Asymptotes, on the other hand, are located at x values that would make our function undefined. That's where asymptotes come from. So these are very commonly found in functions that are made up of fractions, where you have x's in the bottom of your fractions, and there are certain values that you can't let x be equal to because it would make the bottom of your fraction equal to 0. So asymptotes are closely tied to domain. In order to find asymptotes, you set the denominator of your function equal to 0. So this is our first step. You find your critical numbers by setting your numerator equal to 0, and you find your asymptotes by setting your denominator equal to 0. Then we're going to draw an x-axis that's broken into intervals. The critical numbers and the asymptotes represent the breaks in our intervals. And this will make more sense when we do an example. Each of those intervals represents a place on the graph that we have to test for above the axis or below the axis. So within that interval, we choose a test point. It's just an x value that's within that interval. We plug our test point into f and simplify it. If we end up with a positive number, that means that it's above 0. So it would be part of the solution if the question we're asking is whether our function is greater than 0. If our resulting value is negative, then we would be below the axis, we would be less than 0, so that would be not part of the solution. Now, these two parts here are only for answering f of x is greater than 0. If we have a different type of symbol, like a less than symbol, then 4a and 4b would be different. Okay, so we'll just deal with that in examples as it comes up. Let's start with question 1. The steps we just talked about are not going to make a whole lot of sense until we put them to practice. So we have a function. It's a parabola. We don't know what it looks like. So it's a positive upward-facing parabola. We can guess it kind of looks something like this, but we don't know where it is. We're looking for the places where f of x is greater than 0. So that would be this area and this area. But we don't want to find this graphically. We want to find it algebraically. So the important points we have to find are these critical values. We have to figure out what they are. So here's how we set up a problem like this. We want to know where 6x squared plus 27x plus 27 is greater than or equal to, just greater than 0. The first thing we do is we find our critical numbers and our asymptotes. To find critical numbers, we set the numerator of our function equal to 0. Well, our entire function is just a numerator, right? There's no fraction here. So for the second part, to find our asymptotes, we won't have any. To find asymptotes, you set your denominator equal to 0, but we don't have a denominator, so we don't have to worry about that in this problem. So let's focus on critical numbers. In order to figure out what x is here, we have to solve for x. So you can do that in a number of ways. You can factor, you can use the quadratic formula, you can complete the square and solve for x that way. You could even plug these into a calculator and look at it on a graph if you end up with nice, neat numbers, although that's kind of hard to do if your numbers are decimals or square roots, things like that. So I'm going to do it by factoring. So I'm going to factor out a 3. That leaves me with 2x squared plus 9x plus 9 equals 0. Then I'm going to factor this into two binomials. We can use the AC method. I normally can just do these in my head pretty quickly. And then we'd have to set each one of these equal to 0. So we get 2x plus 3 equals 0, and x plus 3 equals 0. We end up with x equals negative 3 halves, and x equals negative 3. So we don't have any asymptotes, but we have two critical numbers. Step 2 is to draw an x-axis and to break our x-axis into intervals, and those breaks will occur at our critical numbers. So we've got negative 3 and negative 3 halves. Negative 3 is going to be on the left, right, because it's smaller, and negative 3 halves will be to the right of it. So we are looking at three different intervals. The interval to the left of negative 3, the interval in between negative 3 and negative 3 halves, and then the interval to the right of negative 3 halves. What we have to do now for our next step is pick a test point in each interval. So basically, we're just going to pick any number we want that's to the left of negative 3. How about negative 4? Then we're going to pick any number we want in between negative 3 and negative 3 halves. So how about negative 2? Because negative 3 halves is just negative 1.5. And now we're going to pick a point to the right of negative 3 halves, any point we want. 0 is usually an easy one to use if you can use 0 in one of your intervals. It's time to test our test points. What exactly are we testing? So all of the values in this section of the interval are either going to be above the x-axis or below the x-axis. Or in other words, they're going to be positive above or negative below. So we're going to take our function and we're going to plug in our test points. So let's do negative 4 first. We plug in 6 times negative 4. Let's do this in green. 6 times negative 4 squared plus 27 times negative 4 plus 27. And we're testing to see if that's greater than 0, because that's what our question is asking us for. If the answer is yes, then the entire interval that negative 4 is a member of is all part of your solution set. So plug this into a calculator. When I do that, I get 15 is greater than 0. That is true. So all of these points on this side of negative 3 are part of my solution, going all the way down to negative infinity. So this whole section is part of my solution. Now we're going to test the next test point, negative 2. So we'll plug in 6 times negative 2 squared plus 27 times negative 2 plus 27, and we're testing to see if that's greater than 0. If you plug this into a calculator, you get negative 3 is greater than 0. That is not true. So this whole interval, everything in between negative 3 and negative 3 halves is a no. If we had picked any point in this interval, they will all end up being greater than or less than 0. They would all end up being negative numbers. So none of those points are going to be in our solution set. One more point to test. We'll plug in 6 times 0 squared plus 27 times 0 plus 27 is greater than 0. Is that true? Well, this simplifies down to 27 is greater than 0. That is absolutely true. So these points are all a yes as well. So all of these points going all the way up to positive infinity are part of our answer. Now let's talk about our boundary points, these negative 3 and negative 3 half points. Are these part of our answer? Well, negative 3 is a place where our function is equal to 0, But that's not what we want. We want places where our function is strictly greater than 0. So this is not part of our solution. And the same goes for negative 3 halves. At negative 3 halves, our function is equal to 0, but we don't want where it's equal to 0. We just want where it's greater than 0. So this is not included as well. So reading our x-axis from left to right, our answer set goes from negative infinity all the way up to negative 3. Negative 3 is not included, so we put parentheses. And then union from negative 3 halves not included, so we use parentheses, all the way up to positive infinity. And that's our answer. So let's figure out how to type this in. Our intervals, they even gave us parentheses here, so they knew we were going to need parentheses. Our answer goes from negative infinity to negative 3 and negative 3 halves up to infinity. So that was for f of x is greater than 0. Now they're asking us for where f of x is less than 0. So it's basically just going to be the exact opposite. We already know that all of the spaces on our x-axis that I just indicated in green, those are places where my function is greater than 0. So the place where my function is less than 0 will be right here in between. Careful though, because negative 3 and negative 3 halves is where my function is equal to 0, so those still won't be included. So my interval here goes from negative 3 comma to negative 3 halves. And that's it. So we put in negative 3 halves, and this is not applicable. We don't need these. And we're done. Question number 3 is very similar to question number 2, but this one's already factored for us, so that's going to make our jobs a little bit easier. So we start off with f of x equals x plus 1 times x minus 3 times x minus 4, and we want to know where this is less than or equal to 0. So first we start off by finding our critical numbers. That is going to be where our function, its numerator, which is everything in this problem, is equal to 0. We're also going to look for asymptotes, but in this problem, we don't have any denominator, so we won't have any asymptotes. So to solve for our critical numbers, since it's already factored for us, this is really easy. We can just split this up into 3 separate little mini equations. X plus 1 equals 0, x minus 3 equals 0, and x minus 4 equals 0. That'll give us x is negative 1, x is 3, and x is 4. So now we draw an x-axis, and we're going to split our x-axis up at our critical numbers. So we start with negative 1, and then we have 3 and 4. So this problem has 4 separate intervals, and we have to pick 4 separate test points. So let's choose test points from here, 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 and here. How about negative 2, 0, 3.5, and 5. Just try to pick numbers as small or as clean as you can. Sometimes you have to use a decimal, like between 3 and 4 we had to use a decimal there. But try to keep your decimals as simple as you possibly can. Now it's time to plug in our test points to test for whether our function is less than or equal to 0 at these points. So we'll plug in negative 2 plus 1. We're testing our first point, negative 2. Times negative 2 minus 3 times negative 2 minus 4. And is that less than or equal to 0? Your calculator is your best friend here. Let's see, we get -1 times -5 times -8, which is -40, less than or equal to 0? That is true. -40 is less than 0. So all of these points over here are a yes. Everything in this interval. Now what about at the point -1? Our inequality says less than or equal to 0. So at this point where -1 is equal to 0, that will be included in my interval. Moving on to the next value, we're going to plug in 0 as our test point. So we get 0 plus 1 times 0 minus 3 times 0 minus 4. Is that less than or equal to 0? Well, that'll give us 1 times -3 times -4, less than or equal to 0. Positive 12. That is not less than or equal to 0. So no, these are not included in our interval. Moving on to our next test point, and this is where it starts to feel a little tedious. 3.5 plus 1 times 3.5 minus 3 times 3.5 minus 4. Is that less than or equal to 0? Time to pull out a calculator. So we end up with negative. It's a negative number. It's a negative nasty decimal. Is a negative number less than or equal to 0? Absolutely. So this is a yes. All of these points in this interval are going to be included in our answer. Also, let's look at the endpoint 3. At the point 3, our function is equal to 0, which is okay because this says less than or equal to 0, so this will be included, and for the same reason, this will be included. All right, finally, let's test our last point. We're plugging in 5 plus 1 times 5 minus 3 times 5 minus 4. Less than or equal to 0? Let's find out. We get 6 times 2 times 1. No, we end up with a positive 12, which is not less than 0. So this side is also a no. So the totality of our intervals here, of our solution set, go from -infinity up to -1, which is included, union 3, which is included, to 4 in another bracket. So our answer, they even told us here, they gave us our parentheses and our brackets for us in the problem, the way they posed their question. So we just needed to figure out what A, B, C, and D were. So A is -infinity, B is -1, C is 3, and D is 4. They're just asking us to list them left to right. These are tedious problems that require a lot of calculation, but your calculator is your best friend on these. They can save you tons of time. Okay, so on this question, I want to point something out. First, we're going to be looking for where our function is greater than or equal to 0, and then we're going to be looking at where it's less than or equal to 0. So I'm going to kind of be answering both questions at the same time. So first, we're going to start by finding our critical points, or our critical numbers. That's where we set the numerator equal to 0. So 5x squared plus 8x minus 4 equals 0. And then we also have to find our asymptotes, but there is no denominator here, so we're not going to have any asymptotes. So I know it's getting a little frustrating that I keep mentioning this, but I haven't shown you an example yet. But I think 1 or 2 examples later, we're going to get to one with an asymptote. So let's solve this. We can solve it by factoring. 5x. Oh, I don't know what just happened. 5x, x, 2, plus, minus. Okay, we can split up our factors into two separate mini equations. And we end up with x equals 2/5 and x equals -2. These are our critical numbers that we use to divide up our x-axis at the points -2 and +2/5. So we're going to pick a test point within each of these intervals, starting with, let's do -3, 0, and +1. We have to plug these test points into our function. So we're going to start with the -3. We'll do 5 times -3 squared plus 8 times -3 minus 4. When we plug that in, I guess I should actually do this. We end up with +17. Is that greater than or less than 0? It's greater than or equal to 0. So instead of actually deciding on my intervals right now, whether they're part of my answer or not, I kind of want this answer to work for both parts of this question. So we're just going to say that these values are greater than, meaning they're above 0. So I'm just going to make a little mark here to indicate that my function values are kind of above the axis. For the next part, we're plugging in 0. So I'll do 5 times 0 squared plus 8 times 0 minus 4. That's going to simplify to -4. Well, these values are certainly less than or equal to 0. So that means our function's kind of down here below the x-axis. And I don't know what shape it takes. Maybe it's like super squiggly and then it comes back up. We don't know what it looks like, but I'm just going to indicate with some shading that my function is below the axis on this part. And then finally, we're going to plug in 1 to our function, which will give us 5, 13, 11. 11 is greater than or equal to 0. So that's going to be above somehow. And we don't know how it's shaped, but we've got above, below, above. So we can use this information to answer question 16. Part A asks us, which of the following intervals accurately represents the solution set of f of x is greater than or equal to 0? So that would be from -infinity all the way up to -2. -2 would be included because it says greater than or equal to 0. Now, none of this next stuff is included because that's all below, but then we pick it back up at 2/5 all the way up to +infinity. So we're looking for parenthesis bracket, union, bracket parenthesis. So parenthesis bracket and bracket parenthesis. So it's this one right here, this second option. And then they want us to put in A, B, C, and D. Now they're flipping the question around on us and asking us, for which of the following intervals do we represent f of x is less than or equal to 0? So I'm going to erase what I wrote. And now we're going to look at where we're less than or equal to 0. That would be starting at -2, going up to 2/5, and we would need brackets around it because -2 and 2/5 are both where our function equals 0. And we want to know where we're less than or equal to 0. So we're looking for this option. A and B are -2 and 2/5. C and D are not included in this problem. Okay, this video is getting very long. I hope you have been able to kind of fast forward and you haven't had to watch the whole thing. But now we're going to finally see a problem that has a denominator. So we want to find where our function is less than -2. We have a problem. Everything we've talked about today is how we solve for less than 0 or greater than 0. We have to have 0 on the right-hand side. You have to have 0 here. So we have some prep work we have to do before we can even solve this problem. So we start off with -3x plus 5 over x minus 3 is less than -2. We've got to move the -2 over to the left. So we're going to add 2 to both sides, which will give us -3x plus 5 over x minus 3 plus 2 is less than 0. Now, this is untenable. We cannot find asymptotes when we're dealing with a problem like this because our numerator is broken up into separate chunks. So what we have to do is combine these two terms into a single fraction. That's going to require finding a common denominator. So we need to multiply this by x minus 3 over x minus 3. That'll give us -3x plus 5 over x minus 3 plus 2x minus 6 over x minus 3. And then finally, since we have a common denominator, we can combine this into a single fraction. So -3x plus 5 plus 2x minus 6 all over x minus 3. And that simplifies. So -x minus 1 over x minus 3, less than 0. So all of that prep work was to get it so that we have a numerator, a denominator, and a less than 0. So now we can start on our steps. We haven't even started the problem yet. Yeah, these are fun. So our steps are find the critical numbers. I'll actually write it out. And find the asymptotes. The critical numbers come from the numerator, so -x minus 1 equals 0, and the asymptotes come from the denominator, x minus 3 equals 0. So to solve for x on our critical number side, we're going to add 1 to both sides, and then we're going to divide both sides by -1. And on the right, for the asymptotes, we're just going to add 3 to both sides. So we have a critical number and we have an asymptote. I'm going to draw an x-axis, and we're going to mark both of these on our x-axis. So -1 is a critical number. That is a place where my graph crosses the x-axis. So my graph actually passes through the x-axis at that point. The other point, 3, is not a place where my graph equals 0. It's a place where my graph is undefined. So instead of drawing a solid line here, I'm going to put a dotted line. So I've got a break at 3, and I've got a critical number at -1. Both of these places still cut my axis up into separate intervals, but I'm drawing it like this to remind myself that my function is not equal to 0 at this point 3. In fact, my function is not equal to anything at that point. My function is undefined at that place, and that's what the asymptote dashes kind of represent to me mentally. Let's pick some test values in each of our 3 intervals. How about -2, 0, and 4? We have to test each of these. We are going to test -2 minus 1. Oh, I'm doing the wrong thing. I guess we could test that. Sorry. So we're going to plug in -2 minus 1 over -2 minus 3. Is that less than 0? So that's going to give us 2 minus 1, which is 1 over -5. We end up with -1/5. That is definitely less than 0. So yes, this interval is part of our solution. So less than 0. So we're kind of down here below our graph, or below the axis. So these are less than 0. Going all the way down to negative infinity. Since our function is asking just for strictly less than 0, it doesn't include this negative 1. So we're going to have a big open circle here because negative 1 is not included in our answer. Let's test our next point. Now we're going to plug in 0 for x. So I'm plugging in negative 0 minus 1 over 0 minus 3. Is that less than 0? So we get negative 1 over negative 3, which is positive 1/3. Is that less than 0? No. So these values within this interval are not part of the solution. One more point to test. Now we're going to plug in 4. Negative 4 minus 1 over 4 minus 3. Is this less than 0? When we get negative 5 over 1, that is definitely less than 0. So yes, these are less than 0. So this section of our x-axis is absolutely part of the solution. Remember though, this is not. We get an open circle there. So if we want to convert this into interval notation, we start at negative infinity all the way up to negative 1, parentheses, union, and then parentheses 3 to infinity. So our answer needs to have just parentheses in it. This one right here. And our A is negative infinity, B is negative 1, C is 3, D is infinity. Lengthy problem. One more to do. We can handle this. I know this has been a long video, but question 10 is very much like the one we just did. Actually, it might even be a little easier. So the first thing I want to point out is that this is not a 0. We have to make it a 0. So we're going to start with some algebraic manipulation to get a 0 on the right. I'm going to write the bottom as x minus 5, just switch those around because it looks a little funny to me. So if this is greater than or equal to negative 2, we need to add 2 to both sides. Don't worry, it's not always 2. I don't know why both of these problems just so happen to be negative 2. All right, so we'll have a plus 2 is greater than or equal to 0. Now over here on the left, we need to turn this into a single fraction. So this is a 2 over 1. We need to find a common denominator, x minus 5 over x minus 5. That'll give us our common denominator. So we'll have negative 4x plus 10 over x minus 5 plus 2x minus 10 over x minus 5. Greater than or equal to 0. We have a common denominator, so we can add the tops. We end up with negative 2x, and the 10's cancel over x minus 5. Okay, we finally got a simplified version of our problem that has 0 on the right. So we can move on to step 1. Yeah, what we just did, that was step 0. So step 1 is find your critical numbers. Critical numbers are numbers we get when we set the numerator equal to 0. And we also need to find asymptotes. Asymptotes are numbers we get when we set the denominator equal to 0. So if we do this, our critical number is just going to be x equals 0. Our asymptote will be x equals 5. So let's draw an x-axis and mark these two places on our axis, starting with 0 is an x-intercept, but 5 is an asymptote. So I'm going to do a dotted line there to remind myself that my function does not cross through at that point. In fact, that's a break in my graph. So pick some test points. We'll do negative 1, 1, and 6. I try to keep my numbers as small as possible. Time to plug these in. So we'll plug in negative 1 first. Negative 2 times negative 1 over negative 1 minus 5 Is this greater than or equal to 0? Well, that'll give us positive 2 over negative 6. That is a negative number. So that is not greater than or equal to 0. So the points over here are a big no. Let's try our next test point. We're plugging in 1, negative 2 times 1 over 1 minus 5. Is that greater than or equal to 0? Well, we end up with negative 2 over negative 4, which is positive 1/2. That is definitely greater than or equal to 0. So these points are a yes. Everything in between here. Is 0 included in this interval? Well, at the point 0, I guess I should indicate it. Yeah, at the point x equals 0, our graph is equal to 0, which is okay. That will be part of our solution set. So we can fill this in and include 0 in our answer. We cannot include 5. You can never include an asymptote point in your answer because your entire function is undefined at an asymptote. All right, one more to test. Negative 2 times 6 over 6 minus 5. That'll be, is that greater than or equal to 0? That'll be negative 12 over 1. That's a negative number, so that's not greater than or equal to 0, so this is a no. If we want to rewrite this in interval notation, we'll start at 0 with a bracket, go up to 5 with a parenthesis, and that's it. So we're looking for this style of solution where a is 0, b is 5. Okay, longest video ever. I hope that was helpful. Please let me know if you have any questions as you're working on your homework problems. Good luck.